Imagine it is the year 1905. One day, the clock on the tower in Bern, Switzerland, is running a little late, 2 minutes, to be precise. For that reason, a man who lives near the tower does not wake up at the same time he usually wakes up every day to go to work. Realizing the mistake, he gets a little nervous. It takes him a little longer to get dressed, get his coffee and leave the house. He leaves 5 minutes later than usual. He gets ready to cross the street. In the meantime, a banker unveils his new car without knowing that it has a small malfunction in the brakes. Our man, still distracted, crosses the street and doesn't see it coming. The man is run over and dies. This man is none other than Albert Einstein. That year, Einstein should have published 4 papers that would be the basis of modern physics. Innovations like GPS, TV screens, the semiconductors that allowed us to create computers, never happen. The computer, the laptop, the phone you're watching this video on never come into existence. In this video, neither. This sequence of events is an example of what is known as the butterfly effect, a manifestation of chaos theory. For many centuries, the world was explained through the laws of Isaac Newton and classical physics. According to these laws, if the current state of an object is known, its behavior in the future can be predicted with relative ease. Chaos theory challenges this deterministic view. Everything is no longer predictable, nor does it work like clockwork. Since the 1800s, mathematicians have been putting forward the idea that not all phenomena could be predicted by Newtonian laws. But a meteorologist named Edward Lorenz made chaos theory a visible phenomenon. It all started in 1961, when he was working on a mathematical model for weather forecasting. Lorenz would input data such as temperature, humidity, pressure, and wind direction into his computer. His computer would draw a graph modeling what the weather was going to be like, not always accurate, but very close to reality. That morning, Lorenz decided to check some results. He slowed down the computer, to save time, entered the numbers himself, and went to get a cup of coffee. When he returned, the graph was incredibly different from the original. At first, it started out quite similar, but in the middle it presented a completely different trajectory. Surprised, he checked the numbers. He found that the number he had entered was 3/10 less than the one used by the computer. That difference, which altered the trajectory so much, is equivalent to 1 particle of dust on the Eiffel Tower, or 1 feather less in the weight of a duck. Lorenz deduced that this experiment was not a special case, that there were systems in which very small differences produced, over time, monumental changes, making everything seem unpredictable. That the flapping of a butterfly in Brazil could, in theory, produce a disturbance sufficient to cause a tornado in Texas. That is to say, no matter how well we know the laws of nature, there are no measurements that offer us perfect data that allow us to determine the position and velocity of each of the atoms in the universe. This inaccuracy in our calculations makes predictions difficult, one of the reasons that makes long-term forecasting impossible. But chaos is not the same as disorder. While chaos makes predictions difficult, the universe is not random, and we live in a universe in which effects follow causes. And no matter how chaotic it may seem, a system always follows a trajectory to certain points. For example, in the calculations Lorenz used for his model, the trajectory to those points created a pattern that looked like the wings of a butterfly. Understanding these patterns of chaos has practical applications. In the stock market, it reminds us that a slight fluctuation can cause a crisis in the market, and that is why we cannot speak of predictions, but rather of probabilities. In the human body, it allows us to understand the chaotic behavior of a heart with cardiac arrhythmia. Even in human behavior, the butterfly effect serves to analyze social phenomena. For example, how trolling on social networks can be triggered by a single negative comment. Our universe continues to obey the chains of cause and effect. The sun will continue to rise every morning. The airplanes we build will continue to fly. Ultimately, chaos theory introduces an element of uncertainty into our reading of the universe. It highlights the limits of our knowledge.